Hey guys, it's Finn. In this video I'm going to talk about the Softmax activation function and how it's very similar to the Sigmoid function that we have already seen. So let's get started, but before I talk about the Softmax function itself, I need to talk about something that is called probability. And you all probably know what probability means, and it pretty much means that we have a value in between 0 and 1 that determines how likely it is that something happens. Now, we had the sigmoid function and the output was between 0 and 1. So you could say, yeah, the output is somewhat like a probability. But there's a huge problem with the sigmoid function in terms of probability. Um, let's say we have 5 outputs and each output is roughly, let's say, 0.8 or 0.9 or even very close to 1. That doesn't make sense to you if you have 5 outputs and each output has a probability of 0.8, because if you have a probability, the probability of each class needs to sum up to 1. That's like you can have, what would make sense if one output has a activation value at the end of, let's say, 0.8 and another one has of 0.1 and another one has also 0.1. So that the probabilities sum up to 1, and that's how basic probability also works. So sigmoid clamped the value in between 0 and 1, but it does not represent the probability of something happening. What we usually did is we took the sum of the wakes times the previous output and plugged that into the sigmoid function. This sum that we just calculated is pretty much like it's like the activation, but not after. It's like before we put it into the activation function. So what we're going to do is we are going to find a activation function that can deal with real probability. And yeah, that's like what we just had before. Let's say we are taking the input 1, or like the sum that we just had over the wakes times the previous output is 1, 2, 3, 4, 5, 6. Like we have 6 neon, and the sum for the first neon is 1, the sum for the second neon is 2, and so on. Then after applying the sigmoid function, we get 0.5, 0.73, and so on. And this doesn't make sense to you because, like, how could the last neon have a probability of 0.99 and the fifth neon could have a probability of 0.98? That's just not intuitive. That doesn't make sense. They don't sum up to 1. So what we want instead is we want something that gives us an output like this. So the smallest value has the smallest probability, and the highest value has the highest probability, and they all sum up to 1. So how are we going to do this? We're going to use the softmax function, and it looks very complicated when you search on it on the web, but actually it's really easy to implement and to use and to understand as well. So this is how it looks. Well, this looks kind of complicated, but yeah, like what we are putting in right now is we are putting a vector in, and that's probably the most confusing thing about it. Let's get one step back. If we calculate this output, we need to take care of all the values. So we need to take an input vector, and we're dealing with one specific value. So the softmax function is fi. So fi of vector I is the index of the output. So let's say f2 would be the 0.009, and a would be the input. And the formula for that is that we're taking e to the power of ai. That's like the i's input. For example, let's say we're calculating f, or I will just make an example on that. We're taking the input index to the eth power, and we're dividing by the sum of all e's to the ak's power. So let's make an example with numbers, and would look something like this. So let's take like the same numbers that we just had. The first thing that we're going to do is we're going to calculate e to the power of a, and we're doing this for each value in a. So we would end up with something e to the power of 1, e to the power of 2, e to the power of 3, and so on. It would look something like this. And this is already like the top part of what we just have. The next thing that we're going to do is we're going to calculate the bottom part. Like, it's simply the sum over all these values. And while it would be just like added, I would just add them up, 2.72 plus and so on until we reach like the final value, and this adds up to roughly 600. And we are pretty much done with calculating all these values. We just need to divide this number, for example, by this sum, and we get the activation output for one specific index. So for example, f1 um, at a or of the vector a would be 2.72 divided by 600, and yeah, it would look something like this, and this would have a probability of 0.004. Same for the f of 6 of f6, would have a probability of 63% roughly. And um, well, that's like the basic understanding of the softmax, but there's also a very important thing when you want to actually implement the softmax, and it's a derivative. So usually you're putting in a vector and you're getting out a vector, and this means that in theory, you can't just like take the derivative. You need to take the derivative in multiple directions in space, but that's like very complicated if you think about it in the mathematical way. But actually, the if you can write it down to like how we would like to have it, and look something like this. This might even still look too complicated, so I'm going to remove the I and the A inside. So we are just assuming that like each the softmax function in a layer has the same input, and well, I'm just going to ignore the I right now. So it might look something like this: that the derivative of any function of a near or of a softmax function of a near in a softmax layer is equal to the output times 1 minus the output. And you have already seen this, and this is like the exact same notation as we had for the sigmoid function. And well, yeah, actually they're really similar. And I've somewhere read that you can transform one into another one sometimes. So yeah, they're very equal. But there's a huge difference when you want to use them, and it's the following. Usually, let's say a network is something that predicts something, and the amount of prediction that it can make is what we call classes. So let's say we have the MNIST dataset. It can predict 0, 1, 2, 3, and so on. So we would have 10 classes. Um, if we have only 2 classes, we would not use the softmax function. We would just use the sigmoid function for the output. Like usually, I didn't mention that yet, but the softmax is only something for the output layer. We wouldn't use that in any hidden layer, just for the output layer. Um, if we have 2 classes, we would not use the softmax. We would use the sigmoid, because I think I'm not sure about that, but I think when we have only 2 output classes, they are pretty much the same. However, if we have multiple classes, like 10 classes, like we had with the MNIST set, the sigmoid worked, as we have seen, but the softmax works way better because it will give a true probability for each class, and this is exactly what we want and what is intuitive for the human, and it works really good with the PC as well. So if you have any questions, just ask me in the comment section, and I will try to answer them as quickly as possible, and I hope to see you in the next video.